Thank you very much. Super excited to be here. Excited to talk about infrastructure as code with Terraform. What I actually want to talk about is like everything as code, not infrastructure specifically as code with Terraform. Talk about what else Terraform not only can be used for, but what else do we actually see Terraform being used for that's not just a cool demo, but actually really, really helpful to various companies. And it really helps you better understand sort of the power of something like Terraform. So we're going to get to that, but we're just going to start with infrastructure as code just to get a basic understanding. So I got an introduction. This isn't getting next. There we go. I got an introduction. My name is Mitchell. I'm one of the founders and CTOs of Hashimoto. If you haven't heard of Hashimoto, we make a bunch of tools that you maybe have heard of. I'll name them all, but the only one I'm going to talk about today is Terraform. But Vagrant, Packer, Surf Console, Terraform, Vault, and Nomad, those are all open source tools that we've made. I'm one of the creators of all of them, so I'm happy to answer questions about any of them if you catch me after the talk or anything. But today is going to be about Terraform. And before I start, I also want to give a quick disclaimer that, of course, I founded a company behind these tools, but what I'm going to talk about today is completely open source, liberally licensed. I will not mention or talk about any commercial sort of software. I really think it's important when I come to community events that everybody be able to sort of take the talk that I give and take something away and be able to actually use it sort of without limits. So the talk today will be all that. So let's go ahead and get started. And to talk about this, I'm going to break it down a little bit into two sections. First, I want to explain infrastructure as code, and then I'll explain Terraform, and then finally I'll explain how Terraform can do a lot more than that, building on these principles. So let's first start by defining infrastructure as code. And this will be relatively quickly because I think a lot of people are familiar with it now. So basically, if we look back at sort of the maturing stage of infrastructure and infrastructure management, you can see a long history. So starting at the beginning and not too long ago, everything was pretty manual. You could log into a server. If you needed to start a process, you would start the process. If you needed to edit a file, you would just edit the file. You just did whatever needed to be done, and everything was manual. That's pretty easy. Very, very shortly thereafter, we got basic automation, basically with the realization that we could have these Turing-complete languages to run scripts for us, using tools like Bash and Python and things like that. We started building automation around setting up these machines. This was both to make us more productive, but also because there was more machines, so we had to be a little bit better about it. And in this sort of era, these were like the secret sauce, right? Like everyone had their individual Bash scripts that made them much better than other sort of operators at the same time. Soon we saw the rise of machine virtualization, and the really important thing that happened with machine virtualization was we saw also a jump in the number of servers we had to manage. I remember one of the first jobs I ever had learning like about sysadmin was probably like 15 years ago, and it was a very high traffic website, but we had 5 servers, right? And it was all manual and all scripts. And that was fine. There was a lot of traffic, 5 really expensive, really large servers, and then we started making the switch to virtualization, and it changed everything because suddenly we needed automation because we were slicing up these big machines into a lot of little ones, and we needed a better way to just manage that and manually SSHing in and running our scripts wasn't cutting it anymore. And then quickly, because of sort of the success of virtualization, we of course saw the rise of cloud, things like Azure, Oracle, Microsoft, AWS, so on. These sort of became, virtualization as a service more or less, and quickly became a lot more than that. But this was a totally new paradigm because now not only do we have virtualization, but we have compute and network and storage basically, milliseconds away from almost any capacity we realistically want. And so not only do we have the problem of a lot of servers that we're trying to automate, but we have the ability, the capability to demand those resources whenever we want. And not a ton of people are using that capability yet, but it is there. And this is further pushing us to think about how do we automate this so we can take advantage of the technology we have available. And then most recently, today we have sort of the idea of data centers, computer with things like Kubernetes and Nomad, Docker in a bit, things like that. And this is really the idea that on top of these servers, if you view them all as one big pool of compute and network and so on, can we just schedule applications to best use those resources? So the grand vision, right, is to use less servers, but those less servers are much better utilized rather than having more servers with one application for each one or something like that. And this is, again, just straining our view of automation, because now it's, in this view of the world, it's completely infeasible to manually manage applications or even assume that an application has a static IP or anything like that. In this world, you know, applications are moving all the time, machines are coming up and down all the time, and in this very ephemeral view of the world, you need automation. And so you would think, like as I went here, if I explained this to someone who doesn't know much about computers, and I have explained this to people like my parents, my fiance, you would think that the whole world, you know, our technical problems are solved. Like everything, we can do amazing things, there's no problems anymore, everything automates and moves on its own. But if you actually look at this, it kind of feels more like this, right? Which is that we went from sort of an era where if I had to SSH into one server and manage one thing, I would be pretty happy, it's pretty simple. More to this right side where it just feels hard. It feels very difficult, and everyone's saying everything should be better, but it feels, you know, hard. And I think this is actually both inevitable but also a good thing, because the reason things are difficult is because we are gaining more capability. We can do things today that are very, very difficult, or were very, very difficult to do 10 or 15 years ago. The capability comes at a cost, which is complexity, and we have to learn how to manage that complexity, and it's relatively new, so we're still learning, we're still building tooling to do that. But I think this is a good thing, because we have to sort of build these capabilities in order to get to a future that we'd like to get to. And nothing's stopping us, right, from still manually managing servers, and some people do that in some cases, but there's so many benefits to cloud and to schedulers and things like that that we'd rather move over there. And so here's a picture of some infrastructure, and this, I don't know if anyone could see it immediately, but this is a really, really standard entry-level website or LAMP stack, basically. This is as simple as it gets, right? Simple in a scalable sense. So what we have here actually, and I don't know if I have, nope, let's not do that. Okay, what we have here is basically a simple website, right? We have at the front, we have a CDN to serve some assets, then we have a load balancer, then behind that we have some horizontally scalable web servers, and then behind that we have horizontally scalable application servers, and behind that we have a database. So web server, application server, database with some static assets. This is super beginner level standard. But if you look at it, each box here is a different thing you need in a cloud environment. This is particularly AWS. So in AWS, this is what you need. And this looks complicated, but the magic of it is that if you do this, if you spin up this blueprint, you will get a website that, assuming you're, you know, let's say it's a basic WordPress blog, you will get a website that's going to scale to, you know, effectively like the 100 biggest website in the world. Like, this will work just fine. You don't have to change anything with the right level of caching and so on. But it's a lot, and it's hard to really understand, and it's hard to think about. But and this is sort of the motivation behind sort of infrastructure as code. What we're getting to is that how do you manage this thing on the left? Well, when we were looking at the problem, the way we thought about it was that, you know, it looks like this. And on the right, this is a database diagram, right? These are tables. I think this might actually be WordPress, I'm not sure. But these are a bunch of tables and their relationships and foreign keys and so on. And it looks kind of similar to us. And when you think about it in that perspective, you know, developers have learned to manage this sort of complexity for a long time. We have ways to represent database schemas and relationships and other sorts of schemas and relationships as code, and we did that for various benefits. And so, you know, it's kind of natural to think, can we turn this into code? And this is really the idea of infrastructure as code. Let's turn sort of this complexity into a codified format and gain all the benefits of representing something as code from that, And this is exactly what Terraform does. Terraform is a tool for taking the code, representing infrastructure as code, and creating the infrastructure from it. And there's a lot of really important reasons for this. When you have something as code in general, it becomes a source of knowledge. So I remember joining a company, maybe it was like 8 years ago, as an operator. It was one of my first full-time operator sort of jobs. And the first few months, I had a lot of questions like, so, what does this server do, and how is the server created, and how does the server relate to these other servers, and where does the configuration come from? And the answer from the people that have been at the company was, oh, for this, I know that answer, oh, talk to this person, oh, I think that was made by this person, and I was just, for the first few months, I was just running around figuring out how anything worked. When you represent something as code, that becomes the source of knowledge, right? You get to move away from this pattern of what I call, oral tradition, which is, if you consider a prehistoric era before we could write, the way we would transfer knowledge was just orally. We would have to tell each other things. And one of the, downsides of that is our memory is fallible. We don't remember perfectly exactly what we did. And so when you sort of orally say, oh, this is how the server was made, this is what it does, you're probably missing something. And it may or may not be important, but it's not perfect. The thing about text and code and being a source of truth is that it's unchanging. It is what it was when you said it, which is probably when you had the most context. You could go look at it. You could look at it without bothering another person. You could sort of absorb this knowledge in an asynchronous way. And so, for example, if you joined HashiCorp's infrastructure team today, we manage some infrastructure, and if you join our team, if you ask how do things work, we would just point you to a set of as-code files. Some of it's infrastructure as code, some of it's applications for schedulers, some of it is some other stuff, but it's in code files, and you can learn how everything works and how everything lays out, all our policies, who can access what. It's all just codified, right? And that becomes a source of knowledge. And if I were to skip to the last one, that source of knowledge, in Terraform's case, is also executable. So the way you describe your infrastructure is also the same format that Terraform reads to create the infrastructure. And so not only is it a source of knowledge, it is the source of truth. It is the actual correct place for what is currently represented. And this is a huge benefit over something like a README. If you say write down everything you've learned, that's great, but the problem with those is that they generally become out of date. And the typical example with that is, how to create development environments and things like that. The README of how to set up your application is usually very quickly out of date. And so how do we reconcile these things? Well, we make the source of knowledge both human readable and machine executable. And then the second point here is once you have something as code, once you have something in a text file, you inherit all the benefits that sort of developers have created over the past many decades. You could use version control. You can now see a history of all the infrastructure changes over time. And as this talk goes on, all these other changes over time, not just infrastructure too. You can see who made the change. You could use pull requests and collaborate on things because it's just text. So Git can diff it. GitHub can manage it. You could talk about the change. You could ask questions. You could review it. And you have it again in the history. You can see who reviewed it, who approved it, who merged it. All this history is there. And none of it is lost to whoever happened to click the button in the UI or something. Maybe you have audit logs for the UI, maybe you don't, but it's a lot harder to keep track of who does things in an imperative UI environment than it is in a version-controlled code environment. And so this is really Terraform. So that's infrastructure as code. That's the basic high-level idea of it. So let's look at how it's made into a reality with something like Terraform. And this talk isn't meant to be an introduction to Terraform talk, so I will go over the basics really quickly, but it's not really the point, so we'll learn some basics. So really quickly, one slide on a high-level overview of Terraform. So Terraform is a tool to manage pretty much anything as code. It's completely open source. Stars are kind of a vanity metric. They don't really mean too much, but they are a good measure of community interest, impact, things like that. So Terraform has a bunch of stars. It also has a lot of contributors. I think this is a lot more meaningful. It's a very active open source project. So from when me and Armand and a couple other people started it 4 years ago to today, on any given day-to-day, there are roughly I want to say 40 or 50 full-time people working on Terraform, and that's not at HashiCorp. At HashiCorp, we maybe have 15 or 20. There's full-time people at Microsoft, there's full-time people at Oracle, there's full-time people at Google that are working on improving Terraform. And not just there too, the other places I'll get to, which is like PagerDuty and GitHub and so on. We have full-time committers that are working on Terraform. So it's a very healthy open source project. But in addition to sort of the full-time people, there's hundreds more contributors on each release that are helping make Terraform great. There's support for over 100 different providers. I'm going to explain what a provider is later, but basically it's a mechanism for whatever Terraform can manage. So easy examples are the clouds, infrastructure, AWS, Azure, GCP, just easy examples. You can manage most of the major features of all those clouds directly from Terraform, but there's also over 97 other things you can manage, and that that should start piquing people's interest because there's not 97 major cloud providers, so that can't all be infrastructure, and actually the vast majority of it is not infrastructure. The goals of the Terraform project were to unify sort of the view of resources and infrastructure as code. So before I was using Terraform, I was using CloudFormation on AWS. I was kind of okay with CloudFormation. I won't say anything more about that. But one of the things that bothered me about CloudFormation quite a bit was I used a lot more than AWS. So I had a lot of AWS, but I also had a different DNS provider, and I had a different CDN provider that wasn't CloudFront. And I could manage my servers and my network layout and VPCs and so on with CloudFormation, and I was like okay with it, but I couldn't manage anything else. And so I ended up writing a lot of Python scripts and Ruby scripts and various other things to manage other stuff, and it just felt weird because if my boss at the time came to me and said, spin up a clone of our infrastructure to run our application, over here, or just in the same place, but just a copy of it, it's not just AWS. It wouldn't run with just the AWS stuff. It needed the DNS entries. It needed the CDN in front of it. And so it felt wrong. And so when we were starting to build Terraform, I really wanted to build a tool that unified all this under a single tool. I wanted to expose a way for individuals and teams to safely create and change infrastructure. And so this was another sort of issue I had with the tools that existed at the time, was that I saw a lot of people representing infrastructure as code to bootstrap infrastructure, but that was about it. For ongoing maintenance for the rest of time, they would sort of manually change the infrastructure because you couldn't trust that the tool that was touching infrastructure was going to do the right thing. So with Terraform, we really wanted a way to make this safe, and I'll talk about that in a bit. And then the last thing, manage anything, I think is related to number one. I didn't want to restrict it to a certain set of things that I thought were sort of the blessed things that it should manage. It should be a truly pluggable environment to support anything other people felt was important, as well as anything that comes in the future that I can't think about. So let's take a look at what some Terraform looks like, and then we'll explain sort of how it works and how you work with it. So this is an example of a Terraform configuration. And this is spinning up an AWS instance and a DNS record. You can see it's a relatively, if you've never seen Terraform code before, I hope and imagine that you kind of have a rough idea what's going on. It's not like total gibberish. It's not like seeing like a wall of assembly or something pop up on the screen. It's pretty straightforward that at the top that I just bolded, there's an AWS instance being created from some AMI, and then at the bottom we're creating a DNS record. So a couple things immediately to notice is that we have two different things represented in one configuration file. We have an AWS record, AWS instance, and a DNS simple record. AWS CloudFormation is never ever going to care or know or deal with DNS simple. DNS simple as a provider probably isn't going to provide an infrastructure as code tool to manage your AWS infrastructure. And so we have two totally different vendors present and able to manage them, and not only manage them, but glue them together. So the green sort of thing I highlighted, you can see I take this sort of dynamically generated public IP address of the AWS instance and use it to populate the A record for the DNS, the A value for the DNS record. And so this is a configuration. It's also declarative, so you can notice that it says what I want, not how to do it. So it just says, I want an AWS instance, I want a DNS record. Terraform's job is to figure out what you currently have, whether it needs to create it from scratch, whether it needs to update something because maybe the AMI changed or the record type changed or something, or whether you're removing stuff. There was an AWS instance in here that you deleted, and so it should destroy it. So it's Terraform's job to figure out how to get from point A to point B, and all you say is what you want, the end goal. Declarative is very important because, in my opinion, this is very much an opinion, but our company's opinion, it's the only sort of method that scales. At a certain point, you have too many people collaborating on infrastructure in parallel, too many teams changing things in parallel, that you can't safely say, go do this, then do this, then do this, and get to where you want to go. You have to have this merged view of this is what it should be, and all this change happening in parallel, and trust the system to get you there. The format I showed you is the human-friendly form of the configuration. I argue it's human-friendly. You could also represent that completely as JSON. This is super important because there are tools out there that generate this configuration, and it's not super fun for a machine to generate human-readable stuff. So you could just generate output JSON. Terraform could ingest a mix. You could have some files that are human-readable, some that are JSON, and it could just ingest that and create infrastructure. And then lastly, I hit on this quite a lot, so I won't go again, but it's text. So version it, put it in GitHub, collaborate, and so on. And so, like I said, you can make changes like this, and you can just make, because it's VCS friendly, you would see something like this in a diff, and when you make a change like this, Terraform would figure out what you mean and do the right thing. So if you change the AMI, what it would actually do is destroy the old AWS instance, create a new one, and then also update the DNS record because the public IP would change. Yeah. So the first command anyone should really learn about Terraform is the plan command. So the plan command shows you what will happen. And this is that idea of making infrastructure change safe that I talked about earlier. When you run plan, it will not modify your infrastructure. It might make some API requests to read information about your infrastructure, but it's not going to modify it. And what it tells you is what it's going to do. And I don't know if I have any examples. Well, I'll show you this. So what it shows you is what it's going to do. And next to anything it does, I follow sort of the Git-like format. If there's a green plus mark, it's something that's going to be created that didn't exist before. If there's a red minus mark, it's something that's going to be destroyed. If there's a yellow squiggly mark, it's something that needs to change, but it can be updated in place. So that means that there's probably not any sort of downtime issues associated with it. And if there's a minus plus, it means that it's something that needs to be updated, but to update it, we need to destroy it and then recreate it. So there might be a window of downtime because of that. And so you could look at the plan and see exactly what's going to happen. You could also save the plan. This will output a binary format. It's not human readable or anything, but you can save the plan, and you could tell Terraform to apply with that plan. What that says is it tells Terraform, reach this desired state, but if your steps that you're going to take differ from this plan, then abort. And so what that does is allows you to look at a point-in-time snapshot of a plan, and maybe your infrastructure is changing in the background, you don't know, and then go and apply it later, and if the infrastructure changed in a way that would have changed the plan, Terraform stops. Because at that point it's doing something you didn't expect. It's doing something that the plan didn't show you. And so you can save the plan and execute it, and that's a very important pattern in Terraform. Plans also show the reasons for certain actions. I think I showed you that a bit, but it shows you sort of whether it has to destroy and create. It also will show you sort of what is causing that destroy, create, what change. And then so prior to Terraform, I'll use CloudFormation as an example. I just didn't see a lot of people using CloudFormation for long-term maintenance of infrastructure. It was used a lot for bootstrapping. And there was one company, one of the first people who adopted Terraform, and actually they publicly talked about it, so I can mention them now, but it was Yelp. Yelp was one of the first companies that adopted Terraform at a very large scale. And I remember going into to their offices in San Francisco and talking with them, and they had two people, if I recall, it's about 4 years ago, they had two people that were the only people in the entire company that could execute CloudFormation. And everybody else wrote CloudFormation, but it had to sort of bubble up to these two people because these two people were the experts who could look at a set of changes and sort of like oracle in a sense and imagine what is CloudFormation going to do if I apply this. And they were the only people that were trusted for hitting that button and hoping that various parts of Yelp don't go down. And Terraform was a really important change for that because one, those two people didn't have to do that job anymore. They could do other things. But also they could enable a lot more people to safely make changes to infrastructure because you could look at the plan, you could use GitHub to paste the plan into a pull request, People can approve the plan, merge, and apply. Right? It's a lot more collaborative that way, and you get rid of these bottlenecks in your company. They've been using Terraform for years now. And so here's an example of what a plan looks like. This would be kind of what you saw if you ran plan against the configuration I ran earlier. It's going to create an AWS instance, and it's going to have a bunch of stuff. So you can see the AMI knows the value. I actually don't think that matches the config, but this was run at a separate time. But it knows the value. But then there's a ton of stuff that Terraform knows that it will know, but it can't know what the value is until it executes it. So these are things like at the bottom, you can see the public IP. This is the way that we're able to do static verification of your configuration. When you reference the public IP, we know that that's a valid value, that we know it. If you typoed public IP with 2 Ps, for example, then we would give you an error before Terraform even ran. And so you can see all this stuff that it's going to know. After you look at the plan, you run an apply. So what an apply does is actually resolves the plan. It executes the changes that the plan would have shown. This is actually going to change your infrastructure. So this is the scary thing in a sense. But hopefully you look at the plan and you kind of know what's going to happen. One important part about apply is it does parallelize things as much as possible. So if you have the AWS instance and DNS record I showed earlier, it's going to do those serially, because it has to. It has to run the AWS instance first to know the IP to do the DNS record. But if you had another AWS instance as well, it would do both of those AWS instances in parallel. It figures that out based on the values that you need. So if you're on apply, this is, again, something similar to what you would see. It tells you what it's doing, how long it's going, and just makes changes. I think I covered this enough, so that's okay. There's also a concept in Terraform called modules, which allows you to take a set of configurations and package them up into reusable components. So rather than having everybody on your team learn, the low-level AWS instance, load balancer, security group, all sorts of things, what you could do is take some complex setup, wrap it up, and then consume a module. So as an example of what that looks like, this is a real module that we published called Console. If you wanted to have a just demo console cluster to show people on AWS, you could do that. I think there's a few other configs you'll have to give it, but if you did that, that's going to set up all the sort of subnets, a multi-AZ setup, multiple console servers that join to form a cluster, and it sets that all up for you, but it'll be roughly like 5 lines, 5 to 10 lines by the time you do it. Modules can also output information. So in this case, we could grab out of that module sort of the names of the autoscale groups that it created, and there's a bunch of other stuff in there. So modules are an awesome way to encapsulate behavior and allow other people to just consume it. Okay, so that's what Terraform is and how it works and what it looks like. Really basic. If you want to learn more about it, just go to the website, play with the Getting Started guide. You could have infrastructure up and running in a few minutes. But what I want to get to is managing non-infrastructure with Terraform. And some people get this really quickly, and some people don't get it till a little bit later, but I think that the realization that Terraform is this generic tool for managing things as code is actually a lot more powerful than just looking at it through the lens of infrastructure, which itself is interesting. So actually, this is a couple weeks ago, right? This is May 12th. So a couple weeks ago, this person tweeted, and I found their tweet, and let me read it. So it says, if you're not A, multi-cloud deployed or planning on it, or B, already married to the entire HashiCorp stack, what is the advantage of Terraform over CloudFormation/Google Deployment Manager? First, I appreciated that this person didn't tell me how terrible of an idea Terraform was and was relatively polite. Most Twitter responses are not that polite. And so given that, I was super excited to answer this because I felt I had a pretty decent answer. And this is a typical, this is a common question. This is just a couple weeks ago, but I get this once a month or something. Like, this is a very common viewpoint. So I responded, I'll paraphrase it, but basically, even people who are multi-cloud often have other services, DNS, CDN, databases, Kubernetes, PagerDuty, GitHub, etc., that they want to manage as declarative code. So it's less about multi-cloud and really more about multi-service in many cases, ignoring some other stuff. And that could be the benefit. And I have some more follow-up tweets with examples for them, but you'll get it in slideshow form. And that was a response. That person ended up responding, finding a specific use case for Terraform that was not infrastructure that, based on their tweet, I think sort of blew their mind. and they seem pretty happy about it. So that's what I want to get into, is let's actually throw away the idea of using Terraform for infrastructure and look at some other stuff. And the key to this is the providers. So providers are the integration point between Terraform and things, whatever things Terraform wants to manage. They expose resources, so this is the glossary of Terraform terminology. There's providers, they expose resources. Resource, for example, like we saw earlier, is AWS instance or a DNS simple record. The resources can represent pretty much anything with an API. And when I say API, I don't just mean like network API, I mean like system APIs too. There's a Terraform provider out there to manage system resources in the same way like a Puppet or Chef would, even though that's not the goal of Terraform, but it can do that. And providers are easy to write. They're actually really great beginner projects. This is also a really common thing, almost on a weekly basis, I want to say. We get pull requests, tweets, and so on about people who fixed a bug in a resource, wrote a new resource, or even wrote a whole new provider. That was their first time ever using Go. And what we've done with providers is we created like a framework. We joke inside it's like a Rails-like framework for creating providers. So you can basically learn Go by just creating create, read, update, and delete functions for anything you want to manage. All the when to call create, when to call read, when to call update, what to update, all that sort of stuff, that's managed by Terraform Core. So you don't even need to worry about that. We figure that out for you, and we just call the right thing, and as long as you make the right API calls, Terraform works. So basically what we're doing with providers is creating a custom one of these, right? And you can create anything you want, and again, you can mix and match them in the same configuration. So a 4-slide brief jaunt through Terraform internals. This is pretty much how Terraform works. There is the core, there's plugins which expose providers, and those providers then communicate with upstream APIs. What the core does is parses the configuration, loads up all the, actually I should go back here. What the core does is parses the configuration, loads up what providers you'll need, starts them, so each provider is actually a separate process. So that's why there's multiple here. So in the case with the AWS record, AWS instance and DNS record, that would be 3 processes running. It'd be Terraform, it'd be the AWS provider, and the DNS simple provider. It starts those all up, establishes sort of an RPC communication between them, and then starts figuring out what needs to be done. And to do that, the core and the plugins sort of have their own protocol, and it's really low level, and this is what our framework manages for you. As a provider author, you would never see these. But the low level interface is basically diff, apply, and refresh. What diff does is says, here's my view of the current state of the world. Don't go verify it, but here's my view of the current state of the world. Here's what the user is asking for. Give me what you would need to do to reach that, reach that state. It's a diff. What apply does is actually resolves that diff. So the result of diff is the parameter to apply. And it says, you told me this was the diff earlier, and this is the current state. Go make this a reality. And what refresh does is says, this is my current view of the state of the world. Please make read-only requests only, and update my state if it's wrong, or verify that it's correct. And that's pretty much all that interface does. And then on the other side, what the providers do is just basic CRUD, right? Create, read, update, delete. That's what that translates into. And so, like I said, anybody could write this green box. This is the extension point for Terraform, and all you actually have to implement are the right side, the create, read, update, delete. The left side is all managed by our framework. If you're more of sort of an algebraic type of person, this is actually how all the terms relate to each other. So there's a Terraform config, which I showed you earlier, which is the target reality. Like I said, it's declarative. It's what you want to get to. There's the state that Terraform maintains, which is its view of the current reality. What the diff does is does your target minus your current view, right? The subtraction. What a plan does is actually shows you that diff. So internally, if you look at how plan works, if you look at the Go code, what we do is actually we call a function called diff that returns the diff structure, and the plan is just a human readable form of that Go structure. So that's the plan. And then apply actually takes that diff and resolves it, makes it reality. So some people find this very intuitive for how to do things, and this is actually how things work internally. And so let's start stepping into our first example. And I think I'm going to do 4 examples, and they're all used in real companies. These are not just hypothetical what I'd like to see people do. I can imagine sort of real examples of where this is used. And so the first one is PagerDuty. There is a PagerDuty provider in Terraform. The PagerDuty company and team maintains it in a partnership with us. So they can release whenever they want. We review their code. We give them advice on how to write better providers. But they write the code full time. So it's official from PagerDuty. And what you can do with this is basically on-call scheduling and notification as code. So PagerDuty is pretty difficult to manage as your company grows because you end up with a lot of calendars, you end up with a lot of users. All the users have different notification methods. There's this huge tree of data that's actually pretty hard to reason about when you get big enough. But what you can do with PagerDuty is represent that all as code. So in this example, we're managing just users. So we create teams, we can create users, and you can see how the dynamic nature of Terraform helps here, that the team requires the ID, and we can just reference that. What a lot of people then do is wrap this up in a module. So anytime a new person joins their company, actually this is a great example at HashiCorp. When you as an engineer actually join HashiCorp, we add a module of you to a GitHub repo. We apply that, and that actually sets up all your GitHub permissions, G Suite permissions, a bunch of other stuff, and we manage it all as code. So you can see exactly how employee onboarding works because it's all represented as code. Same thing with PagerDuty. We manage PagerDuty or on-call schedule here. So you would become a user, and then you can manage things like schedules. So these are actually really complicated. So schedules, I ended up pruning a lot of it, but this thing is probably 5 times longer than this. But in this case, we're creating a schedule, and you can see we can assign users again dynamically. You can just start assigning users and teams, and it's all as code. So PagerDuty is a really cool one, a really common one. The next example is Datadog, or any other monitoring metric solution, I suppose. And this is basically metrics, graphs, and notifications on those graphs as code. Very similar. Just going to quickly dive into it. Here's the example of creating a Datadog time board as code. So, what you want to be able to do is on one side of Datadog, the metrics creator side, is you just dump, data points into a sink, right? You have all these applications that are just dumping data, and it's all going to Datadog, and you have a ton of stuff. And then on the other side, you generally have people logging into Datadog's UI and creating graphs and time boards and notifications just manually. And what you can do with Terraform is take the clicking in the UI, turn it into code, or make a hybrid approach, turn some of it into code, and start managing it that way. So in this case, this is creating a time board for Redis latency, and you can see that what we're showing on the time board is just the average Redis latency per host, and it's all as code. You can also do things like monitors. So here's the example of something that can go critical and warn and notify people. And so here's just another example. This is another one of those things that's really long, actually, in practice. Okay, so the next example is GitHub. I think there's one more after this, but just trying to give you this tour of all these different ways you can use it. So with GitHub, you can actually manage your repo structures, organization, team structures, permissions of what teams could access what repos, and you can do that all as code. This is actually I think this was actually the first non-infrastructure use case that we had for Terraform, because very quickly, both as an open source company with external contributors and a bunch of private repos, we're going crazy trying to figure out what teams did what. I think at one point we had more GitHub teams than we did employees. And we couldn't figure out what, there was core X, there was core Y, and what does core even mean? I didn't know anything. And so what we started doing was abstracting that all out into Terraform. And so we create, actually, I don't have a good example for orgs. We create all our organizations with code. We create all our teams and how they belong to those organizations with code. And then we also assign GitHub user IDs to teams all as code. So if anyone actually in here, I haven't talked to any of you really yet. If anyone in here is a core committer on any HashiCorp projects, you became a collaborator on that project by us editing some Terraform and then it applying in the background. That's how that happens. We do not use the GitHub UI to add collaborators. We do not use it to onboard people into the org. Actually, we have a process that anything that isn't in the Terraform state just gets deleted from GitHub. So if I actually added someone as a collaborator on like Terraform right now, in roughly a few hours, we don't run it that often, in roughly a few hours, you would actually be removed as a collaborator because you just don't show up in the state. We also use it to manage issue labels. So this is actually how we can maintain some parity across all our open source and internal orgs. We have recommended issue labels that people should use to triage and categorize things, and we create them all with Terraform. So this is actually, doesn't look like it, but there's actually a loop that goes over all those and assigns the variable the color, or the issue label the color. And those are actually all the examples. So those are just a few examples of what you could use Terraform for that had nothing to do with infrastructure. If you want to learn more about what Terraform can do, that's the list of all the providers at the top. If you wanted to write a custom provider, we have a new section of the website dedicated to just that, called the extend section. And then if you actually wanted to like have your provider distributed with Terraform, become one of the 100 that's actually supported, you do not need to be a big company to do that. We have tons of individuals that have their providers that we officially put on the website and document, and you could just work with Terraform. There's a program to get that happen. That's free. Like, there's no cost to that. There's just process and red tape, but you can go through that. And the extending part is really neat because you could also support stuff that isn't public, right? Yelp is actually a great example again, because they were one of the first people that figured all this stuff out. Yelp had this old school technique where whenever their infrastructure changed, they had to create a changelog entry in a Git repository. So that was a huge issue in their automation, because if you changed anything in the infrastructure, they had to create a commit with text changes in their Git repository. One of the first really cool use cases of Terraform I saw outside of HashiCorp that wasn't infrastructure was Yelp wrote their own provider to do this for them. They had a resource that actually did this for them that would be super not useful to anybody else outside of Yelp, so they never published it publicly. But they wrote it themselves, and they could use it, and they don't need to fork Terraform or do anything weird, right? It just works because it's a plugin-based architecture, and that's a supported use case. So take a look at that. That is sort of the goal of the talk, so thank you very much.